Hello everyone, my name is Fabian Parra. I'm a research engineer at the Nuclear and Applied Robotics Group, and today I will be presenting our work on visualizing ionizing radiation using virtual and augmented reality for robotics and nuclear education. So, why do we need to visualize ionizing radiation? Well, one of the fundamental challenges in nuclear science is that ionizing radiation is invisible to human eye. So knowing where the radiation is located and how intense it is essential for applications such as nuclear safety, facility inspections, decommissioning, and robotic operations. And although specialized detectors can accurately measure radiation, the data is often presented in ways that are difficult to interpret, especially. It can be challenging to understand where the radiation is coming from or how it relates to the surrounding environment. This is where extended reality can help by making the invisible visible, by allowing users to visualize radiation directly in 3D space. In this presentation, I'll show two applications that we developed. The first one is a virtual reality education platform called RadGame, and the second one is an augmented reality system that visualizes radiation in real-world environments to improve situational awareness in nuclear operations. The first application I'd like to present is RadGame, a virtual reality educational platform developed by the Nuclear and Radiation Engineering program. The idea is to provide an engaging learning environment where users can visualize and interact with different types of ionizing radiation. So traditional educational approaches, such as textbooks, videos, or static demonstrations, often cannot effectively convey the invisible nature of radiation or provide hands-on experience. Using virtual reality, we can create an immersive learning experience that is both safe and accessible. This app can be presented in classrooms, universities, museums without requiring any radioactive material or any specialized laboratory, allowing a much broader audience to explore nuclear science. In RadGame, users are placed inside an immersive virtual environment where they can visualize and interact with different types of ionizing radiation, alpha, beta, and gamma. And users can explore and interact with different scenarios and receive real-time feedback through visualizations and audio cues. Also, interactive panels appear with information about the types of radiation, the radioactive isotope, and relevant facts about the objects. Here I have a list with some everyday life objects that we use for the game and corresponding radiation levels. And on the right, the picture shows the particle system that we use to represent alpha, beta, and gamma radiation with different colors, shapes, and propagation ranges, allowing users to immediately recognize the type of radiation associated with each object. Here is a short video of the walkthrough of the game. The first level of RadGame takes place in a studio apartment because it is a familiar environment that helps learners relate nuclear science to everyday life objects. As the user explores the apartment, they encounter common household objects such as bananas, coffee, smoke detectors, Brazil nuts. So those objects introduce the idea that radiation is not limited to nuclear facilities, but is also present in many aspects of our everyday environment. Another important concept is background radiation. The user can see cosmic particles entering the environment, demonstrating that exposure is not only associated with specific objects, but it's also a natural part of our surroundings. And as the user continues exploring the apartment, they can encounter, for instance, a dog, and interacting with the dog triggers the radiation visualization, reinforcing the idea that radiation is present in living organisms as well. Okay, now I will move to the second application, which focuses on the operational side of radiation visualization. Here I will present the functionality we have integrated into AugRE, the augmented reality framework developed at the Nuclear and Applied Robotics Group. Unlike RadGame, which focuses on education and training, this system is designed to visualize radiation in real-world environments and support applications such as robotic inspections and nuclear operations. The AR application combines several capabilities, including spatial mapping to understand the environment, object detection, particle systems, intensity-based rendering, and we also have integrated data from a ComCom camera to enable visualizations based on real radiation measurements. One of the main goals of this work is to enable human-robot collaboration for radiation monitoring. In hazardous environments, robots can be deployed to perform radiation surveys and collect measurements while reducing the need for direct human exposure. However, this is not to replace the operator, but rather to provide the operator with better information and tools to make decisions. So through the augmented reality interface, we introduce a human-in-the-loop approach where the robot performs the data collection and exploration, while the human remains responsible for interpretation, supervision, and decision-making. In this video, we demonstrate a radiation survey performed by a mobile robot equipped with a radiation sensor. The robot autonomously executes a coverage path while avoiding potentially contaminated areas, reducing the risk of spreading radioactive material. As it navigates the environment, it records alpha radiation measurements and constructs a spatial heat map in real time. The operator wearing a headset can see the radiation distribution directly overlaid onto the physical environment, including areas that may not be visible due to occlusions. This way, the operator can quickly identify radiation hazards and save routes. Similar to RAD game, we included a particle systems representation to visualize different types of ionizing radiation. The alpha, beta, and gamma rays have different colors and propagation ranges to provide intuitive visual cues about their natural behaviors. We also developed radiation fields visualizations to represent how intensity changes throughout the environment, helping users identify areas with higher radiation levels. And finally, using spatial mapping, we can generate a mesh of the environment and project the radiation intensity directly onto it. The heat map representation allows operators to see the radiation distribution in real world and better understand where the hazards are located. The reconstruction environment can also be viewed remotely, allowing users to explore the radiation field from a safe location, avoiding exposure to the hazardous areas. We also integrated measurements from real gamma radiation sources using a ComCom camera, which basically estimates the direction of the radiation source, analyzing the interactions between its scattering and absorption layers. And by combining multiple detections events, it generates a radiation image, and then we project that image into a 3D sphere to have a better spatial and situational awareness. In this final demonstration, we showed the complete workflow combining the robot, the area interface, and radiation measurements from the ComCom camera. Initially, the robot is executing an autonomous survey. The operator then enters the room and using a hand gesture sends a stop command to the robot. The supervisor can explore the area by using the mini-map, which is a scaled-down reconstruction of the environment, and the logos represent the robot and user's location. Now the supervisor points to an area where he wants the robot to inspect, and the robot autonomously navigates to the designated location. Once the robot reaches the goal, the operator can request a radiation measurement from the extended menu. The ComCom camera starts collecting gamma radiation events for around 30 seconds, and basically it is using events and interactions on the scattering and absorption layers to compute and estimate location of the radiation source. In AugRE, the ComCom images are visualized by projecting the 2D texture into a 3D sphere spawned at the camera location. The ComCom image is visualized as a heat map, and blue regions indicates little or not detected gamma radiation, while red regions highlight the direction from which the gamma rays are most likely originating, helping the operator identify the location of a radiation source. The ComCom image is also displayed in the mini-mesh representation, and the operator can interact with it by pinching the sphere to project the radiation texture onto the environmental model, which helps to visualize the location of the source and understand the surrounding radiation conditions. All of this pipeline shows the complete human-in-the-loop concept where the robot performs the data collection and the operator uses XR to interpret the environment and make the decisions. Now the operator can command the robot to continue the inspection and move to a different location. Thank you.